Yeah, okay. Uh, when we're ready, we'll start the test and have you guys do the problems. So tell us when you're ready. Okay, you should have the test up and ready. Uh, and I will see. Okay, we'll be starting very soon. We'll be starting at 5:10 precise, and ending at 6 o'clock. See this? Yes. Now we don't normally use Adobe Acrobat, so uh, but it should still work fine. Okay, so let's jump right into here. First of all, my aim before we get started, I'll say yes. The solutions, well, for any test you do, you would expect to, and this is true of this test, you would expect to be able to see the solutions online. Sure. My aim here is to sort of guide you through the thinking process of doing a problem so that when you read a solution, you can know the solution. But when you when we discuss this, hopefully you'll be able to solve problems like these and understand how do I come up with the solution. So number one, find the sum of all positive integers whose largest proper divisor is 55. So what we want to do is we want to classify what is the largest proper divisor of a number in general. If we have a number n, so the largest proper divisor is going to be, well, it's a divisor of n, so it's n divided by some integer. And a proper divisor means it's not equal to n itself. So it's equal to n divided by the smallest divisor of n that is not equal to 1. So here we have the largest proper divisor of n is, yes, n divided by the second smallest divisor of n. And the second smallest divisor of n is the smallest prime divisor of n. So we see if the largest proper divisor of n is 55, then n equals 55 times a prime, where the prime has to be the smallest prime divisor of n. Now, n already has 5 as a prime divisor, so the smallest prime divisor can only be 2, 3, or 5. And the values we have are 55 times 2, 55 times 3, and 55 times 5, giving 550. Okay, we'll have to move on quickly to get through, but if you have questions, just type it in the chat and I'll be able to answer them. Problem 2. So we've got this absolute value expression where there are 2017 x's in this expression, and determine the sum of all distinct values for which this equals 1. So, well, let's just start by analyzing the expression. Maybe start with fewer x's. Maybe start with 2 x's, see what the absolute value of x plus x and the absolute value of that thing is equal to. Well, if x is positive or non-negative, the expression pretty clearly equals 2017x. So we can focus our analysis for just negative values of x. And well, the absolute value of x equals negative x. With 2 x's, the expression is the absolute value of x plus x. And when x is negative, that would be negative x plus x, and that's 0. So when you've got the expression with 2017 x's, the inner two most x's just equals 0 for negative x. So the expression just it simplifies into the same expression, but with 2015 x's, and so on and so forth. You can the expression, because the absolute value, because let's see if I can draw here. I can annotate. Okay, I'll annotate. So because this thing here is equal to 0, whenever you have such an expression, say with 2017 x's, this it's equal to the same thing, but without the inner two most x. So this simplifies to 2015 x's, which simplifies to 2013 x's, and so on and so forth. And the expression just equals the absolute value of x, which is just negative x. So the solutions are 1 over 2017 and negative 1, giving the value negative 2016 over 2017. Next page. Okay. Can I clear all? Okay. Find the number of integers n between 1 and 2017, so that n minus 2 n times n minus 0 times n minus 1 times n minus 7 is a multiple of 1001. Well, first of all, this is a modular equation. It's a polynomial of degree 4, if you will, but we're not going to expand this and treat it just as a polynomial degree 4, because the factoring is very useful and quite necessary for solving this. But in any case, it's we are solving an equation modulo 1001. So the solutions are going to be residues modulo 1001. So let's find the number of solutions between 1 and 1001 first, and then that will equal the number of solutions between 1002 and 2002. And we would just be, what's remaining would just be solutions between 2003 and 2017. And these we only have 15 values between 2003 and 2017, and any solution there corresponds to a solution between 1 and 15. So that's quite a doable task. So first things first, let's find the number of solutions between 1 and 1001. So we do need to prime factorize here, because it's, so if you've got the reason prime factorizing may seem quite obvious, but the reason it's so important here is, if I could, if we've got, say, an expression, say xy, the product of two terms, let's say, then if we know a prime divides xy, then we know that this implies that the prime must divide either x or y, or p divides y. But the same is not true if we replace the prime with just any number. So if we replace p with 1001, we don't have that 1001 must divide n minus 2 or n minus 0 or n minus 1 or n minus 7. But we do know that each prime, 7, 11, and 13, must divide one of the terms. Not necessarily the same term, but one of the terms. So we can take this separately by each prime. So next slide, there are, so modulo 11, 11 must divide one of the 4 terms, so n must be congruent to 0, 1, 2, or 7 modulo 11. So there are 4 possible residues, mod 11, mod 13, same thing, n must be 0, 1, 2, or 7 mod 13, 4 residues, mod 7. Mod 7 is a bit tricky here. N minus 0 and n minus 7 are the same modulo 7. So we only actually have 3 solutions modulo 7, 3 possible residues modulo 7. That would be 0, 1, and 2. And by the Chinese remainder theorem that tells us that for each triple of residues, say if we want 2 mod 11, 0 mod 13, and 1 mod 7, that is going to correspond to a unique solution modulo 1001. So that is why the Chinese remainder theorem is why we have 4 times 4 times 3, which is 48 solutions modulo 1001. Okay, and the rest is fairly straightforward. We just need solutions between 1 and 15. One of the 4 terms must be a multiple of 13, so that restricts the number of values we need to check, and turns out only 1, 2, and 7 are solutions. So there are 2 times 48 plus 3, which is 99 solutions. Problem 4. So we've got a triangle. We've got a point P that lies on a circle, the circle with diameter AB. And what is the greatest possible area of triangle APC? So it doesn't hurt to draw this. Like I'll draw a rough diagram here. So, whoops. Here is our triangle ABC. This is C, this is A, and this is B. And we've got a circle with diameter AB, so something like this. And we've got a point P. We want to find the greatest possible area of APC. So first of all, how does the area change as P changes for P on the circle? Point here. So what is, you can think of this as, say, locus. In general, in geometry, useful method of thinking is if you just coordinate match this. So here's we want to well, I suppose coordinate matching might be fine because the numbers are designed to be nice, and we'll see why the numbers are nice. But if we can be a bit more lazy and just use our intuition, and that could actually save us quite some time. So in geometry, a useful way of thinking is to consider what elements of our diagram are fixed and what elements are not fixed. In some cases, we won't have things that are not fixed, but we also want to see which points, which points would determine the entire diagram. In other words, if we fix these points, which points satisfy that if we fix them, then the entire diagram is fixed? Well, in this case, it's more of the case of, well, there's one point that moves, that's point P. How does the area of APC change as P changes? Becomes pretty clear that because A and C are fixed, the area of APC is just, well, base times height. It's equal to the base, which is AC, times height from P to AC divided by 2. So if we want to maximize the area of APC, we just want to maximize the area, the distance from P to AC. And with this diagram, it should become pretty clear what point on the circle is farthest from AC. That would just be the point where you can take the perpendicular bisector of the chord, and one of the intersections of the perpendicular bisector and the circle should be our point P that maximizes. Okay, so that maximum distance is just, it's not difficult to calculate. It's just the area, it's just the radius here, plus the distance here, distance from the center of the circle, which is the midpoint of AB, to our line AC. So uh, the distance from the center to that line AC is equal to half the length of the altitude from B to AC. And if we want to find the altitude from B to AC, we can do so by finding the area of ABC. With herons, knowing the side lengths, with herons, we get that the area is 84. And so the altitude from B to AC is 8. So the distance from P to AC is 9. And our area is, yes, indeed, 189/2. Yeah. Okay. We'll have to speed along here. So given that A, B, and C are integers with A, B equals 60, and we've got the third root of unity, omega, finding minimum possible value of A plus B omega plus C omega squared. Now, this is quite a weird problem in the sense that we've got a finite, although not necessarily small, number of triples of A, B, and C, and they're integers, which is quite an arbitrary condition here for an algebra problem. And we want to minimize the value of A plus B omega plus C omega squared. Well, the first thing we might recognize is that if A, B, and C are all equal to 1, then that expression equals 0. So intuitively, because 1 plus omega squared equals 0, we want A, B, and C to be as close to each other as possible. So this suggests we want A, B, and C to be 3, 4, and 5. When we have 3, 4, and 5, our expression would be just 3 plus 4 omega plus 5 omega squared, which is just equal to omega plus 2 omega squared. One thing to note is that if you permute A, B, and C, if you permute 3, 4, 5, the magnitude of our expression actually does not change. So the magnitude of omega plus 2 omega squared is the same as, say, 2 plus omega. In any case, that evaluates to the square root of 3, which is our answer. If you're wondering how we could do this more rigorously, here's how. Let's express z equals A plus B omega plus C omega squared. And we want to find the magnitude of z, the norm of z. One way you could do this is to write omega as -1/2 plus root 3/2i, and omega squared is -1/2 minus root 3/2i. That's a doable thing that is, however, quite algebraically messy, at least a bit more algebraically messy. But another way to evaluate the norm of z is to use z times z conjugate. And z conjugate is just equal to A plus B times the conjugate of omega plus C times the conjugate of omega squared, which is just A plus B omega squared plus C omega. So you could just expand this as a polynomial in terms of omega. Using that omega cubed is equal to 1, we'll get a quadratic in terms of omega. And the expression we actually get is this. AB plus BC plus CA omega squared plus AB plus BC plus CA omega plus A squared plus B squared plus C squared. Which you can subtract out your AB plus BC plus CA from each coefficient, and you'll get our expression, this here, which it's useful to recognize this as half of a sum of squares. And if we just want to minimize the sum of squares, then it becomes pretty clear that 3, 4, and 5 is the smallest you can get. You can't get any smaller than 3, 4, and 5. But I do consider this rigorous approach to be rather difficult to work out in time under time pressure. So the intuitive method is fine in this case. So if you use that, that's understandable. Problem 6. Let's see what we can get through. I'd like to get through at least problem 8. I think problem 9 and problem 10 are more they're less instructive, perhaps, or maybe problem 9, but problem 10 is more of just straight. I won't say straightforward, but direct computation. Okay, in any case, we've got this equation in terms of floors and ceilings and square root, and find the number of such integers n that satisfy this. So let's break this down here. So if we look at just this and this here, they're integers and they're 1 apart if n is not a perfect square. So that's our first observation. If n's not if n's a perfect square, that's a separate case we'll consider soon. But if n is not a perfect square, then the floor and ceiling of square root n differ by 1. So in that case, the equation just becomes, for some value of x, the floor of x plus 1, square root x plus 1 must equal the ceiling of square root x. And it becomes clear that we must have that x or x plus 1 must be perfect square. Okay, so that means that either the floor of square root n or the ceiling of square root n must be a perfect square. Well, let that perfect square be k squared. Let's express n in terms of k. We have that square root n is between k minus 1 and is between k squared minus 1 and k squared plus 1 strictly. So n is between k squared minus 1 squared and k squared plus 1 squared. We also have the case that of when n is a perfect square, and that would require square root n to be also a perfect square. So n must be a perfect 4th power. So putting these two together, n is magical if and only if n is between k squared minus 1 squared and k squared plus 1 squared for some value of k. And n is less than 100 squared. So we count this over k equals 1 to 10. Note that 10 is k equals 10 is be careful of k equals 10 here, because when k equals 10, our upper bound is not 101 squared. Our upper bound is actually 100 squared. But in any case, the counting here is rather straightforward. You can sum them up and you'll get 1330. Okay, let's clear. I'll run through problem 7 really quick and try to get to problem 8. And by then time will be up. Okay, in any case, problem 7. So we start with a cube, and each turn we're going to take each vertex and cut off a pyramid with that vertex as one of the vertices. And essentially, if I could draw this here, let's imagine our cube. If we say take this vertex, then what we're doing is we're cutting out a face like this. We're chopping off that vertex, essentially. And we just want to count how many faces are on the polyhedron after the 5th step. Well, each step, you're going to have the faces, the original faces. Those are still going to be faces. And the new faces that we create are the planes that we chop out near each vertex. So each step, the number of faces increases by the number of vertices. So we just want to count the number of vertices at each step. Well, the number of vertices triples because each vertex is cut off, but it's replaced by 3 vertices along each of the 3 edges that meet at the vertex. We do have 3 edges that meet at each vertex because we'll always have 3 faces that meet at each vertex. So just list the table here. The number of vertices is 8, 24, 72, so on and so forth. And the number of faces is add the number of vertices each time to get 974. Okay, if I may, if you'll humor me, I'll I think I'd like to get through problem 8. It's, I think, one of the more instructive problems on this test. As for problem 9 and problem 10, the solutions are available. Problem 9 specifically is more of a contrived problem, I feel. So just I guess for problem 9, read the solution, know that this is this very specific technique, and if it ever shows up, something very similar should work. In any case, we digressed. Problem 8. So we've got a collection of all the non-empty subsets of 1, 2, 3, 4, 5, 6, 7, 8. Each step we randomly choose 2 subsets, and we replace them either with their intersection or their union. So we can't have repeated sets in our process. So we continue this until we have 1 set left in the collection. What is the expected size of the set? So these problems are expected value problems, and perhaps the most important fact about expected value is called linearity of expected value, linearity of expectation, that is. And here's how we're going to apply linearity of expectation on for this problem. So linearity of expectation says that the expected value of the sum of something is equal to the sum of the expected values of the things. So in this case, we want to find the expected value of the size of the final set. And the size of the final set is just the sum of the number of occurrences that each of 1, 2, 3, 4, 5, 6, 7, 8 appears in, the number of times each of 1, 2, 3, 4, 5, 6, 7, 8 appears in the set. So, and of course, the number of time, the expected number of times, the time that each number appears in the set is going to be the same. So it's just 8 times the expected value of the number of times that 1 appears in the final set. And when I say the expected number of times that 1 appears in the final set, that's really just a weird way of saying the probability that 1 is in the final set. So now we just focus on, we ignore all the other numbers in our collection, and we just focus on the number 1. We want to find what's the probability that 1 is in our final set. So now we just have, forget about all the other numbers. Now our initial sets are just 128 sets of just the number 1. So if I could write here, we've got 128 sets that are just the number 1. And we've got 127 sets not containing 1, so we'll just keep them as the empty set. 128 times those, and 127 of those, that times 127. Now with our operation, each time when we have 2 sets, if the 2 sets are the sets of the number 1, then the set replacing them is just going to be the set 1. The same is true of 2 empty sets. So what about if we have a set of 1 and an empty set? Then the operation is going to be, there's 1/2 chance that the final set is going to be 1, and a 1/2 chance that the set replacing them is going to be the empty set. So we notice that our operation here is just equivalent to taking two sets and choosing one of them to discard. And that in turn is because each set, if you choose two sets, each set is equally likely to be amongst one of the two chosen ones. So long story short, this is just equivalent to choosing a set out of our entire collection of sets at random and discarding it. And the final set, well, each set is equally likely to be that final remaining set. So the probability that one is the final set is 128 over 255. And our answer is just 8 times that, which is 1024 over 255. A final remark, if I may, is notice that the problem did not have to, they did not have to restrict this to be just non-empty sets. They could have just included the empty set as well. There's nothing wrong about the problem nothing in our problem breaks. And if we do include the empty set, then our answer would be 4. The expected value is just 4. So you can see that the only reason they excluded the empty set is to make the answer not so guessable. In any case, thanks for coming. Next week will be another session, but you will be doing a test that I'll be compiling. So it's not a real HMMT year test, but it's more of an instructive test that will consist of several specific techniques that I think are worth discussing. So in any case, thanks for coming. See you next week.